Good morning. Well, today we're going to switch gears a little bit and we're going to talk about functional programming. So before I completely shift gears, I want to say that there's two other areas that I would like to explore, but I'm not sure we're going to have enough time to do it. So one is data encapsulation. And so with that, we would be talking about things like records in a little bit more depth. But and also object-oriented programming. Um, but I feel like for both of those, you have enough experience with those that if we left those, I took those off the table, we would still do a good job of covering programming languages in the course. The two things I did want to expose you to, however, were functional programming and logic programming. So we're going to spend a couple of weeks looking at functional programming, and then probably a week or so looking at logic programming, and then we'll see where we're at. If we have enough time, we might revisit a few other topics. But I definitely want to cover functional programming and logic programming before the course ends. So what we're going to be doing with functional programming is we're going to be working in a language that's called Scheme. Well, technically it's called Racket. It's a dialect of Scheme. It's going to be explored using a development environment from Northeastern University called Dr. Racket. But before we get into using that development environment and exploring the language, I wanted to give you a little bit of background on the idea of functional programming, because functional programming is very different from the kinds of programming that you're used to doing. You're used to doing what's called procedural or object-oriented programming. Functional programming is much more mathematical. And so in order to get a good handle on what this means and why the behaviors of the language should not surprise you, I wanted to talk to you about mathematical functions. All right, so if we wanted to define a mathematical function, there's a couple of things that we would need to do. The big picture of mapping, of defining a mathematical function is what we're doing is we're mapping a set of domain values to a range value. So a way of thinking about this is you've got an X, that's your domain, and then you're going to do some kind of operation on X, apply some function to X, and then you'll get back a Y, that's your range. So let me define what the domain is. This is a set of values. If you have multiple values, like your function processes, say like x0, x1, x2, that's your input to the function, then this set of values would be a cross product. So potentially you're talking about a cross product of sets of values. If you've got a function which processes multiple domains in order to get a result. All right, we also have a range. And this is a function mapping of domain values to some result. All right, and let me talk about what this function mapping is. So the mapping is, well, the mapping, the way the function actually operates can be, well, it can be a bunch of different you can have a bunch of different sort of expressiveness to define how the mapping works. So it might be a table, or it might be an expression, or it might be the function itself. Or it might be another function. So let's do an example of this, all right? So here is factorial. So this is an example, factorial. All right, so we're going to define factorial as f of n, and the function is defined as having the range value, the result of 1, if the domain value n is 0. It is n times f of n minus 1 if n is greater than 0. And it is undefined if n is less than 0. All right, so now, what we've done here is we've defined the mapping of a domain n, which is basically, we can say the domain of n is all integers, to a range of values based on what the domain is. If the domain is 0, we're going to have 1. If the domain is greater than 0, we're going to have this function get, this expression get evaluated, which includes a call back to the function. And if n is less than 0, we're going to say that the function is, or the domain is undefined, or the range is undefined. Return value is undefined. Okay, great. Now, how do you evaluate a function? So that was defined, so evaluate. How do we evaluate? Well, we have the ability to have an expression. We have the ability to have a table. We also have control flow. And the control flow has two components to it. One is we have selection. We have n-way selection. And two is we can have repetition via recursion. Whoops, via recursion. Kind of ran out of space there. Via recursion. Here's what we can't have. There is no iteration. So that means no while and no for loops. And there's some interesting things about how expressions are evaluated, which we'll get into in a little bit. Okay. There's also, let's see. There's also no state. So I'm going to add that. So that's kind of interesting, right? So there's no state. Well, that means that If you call a function or a method or subprogram, subroutine, whatever you want to call it, if you call a subprogram, that subprogram returns, and you can never have a functional side effect when you call a subprogram. There is no memory other than the stack. So you don't have heap variables, for example. So there's no state. That implies that there's no side effects. And there are also, incredibly, no variables. Only function parameters. So there's no concept of creating a local variable when you're doing functional programming. Okay. All right. So let's talk about how functions get used. All right. There's a couple ways that functions can be used, and I just wanted to show you that. So, all right. So let's say I have, a function, cube of x is defined as x times x times x. All right. Now, if I have defined my function as this and I want to use it, what I'm going to do is something called application of the function. So I'm going to say cube of 3. Now, when I do that, x is bound to 3. And so that is 3 times 3 times 3. So the application of the function binds a parameter to domain value. And we see that happening here. The parameter x is bound to 3. There are no variables. I've already said that, but I want to get that clear in your mind. There's no variables. Okay? And you want to think of parameters are basically placeholders for domain values. Okay. Now, let's take a look at something called functional composition. Okay, so functional composition is a function with parameter that is a function. So here is an example of that. So I've got an f of x, which is defined as x plus 2. I've got a g of x, which is defined as 3 times x. And then I have an h of x, which is defined as f of g of x. There's another way to describe this, an alternative way of describing this, which is HG. It looks like hog, but that's just a little symbol. And this, it says, I'm going to just zoom in here for a second. H is defined as F applied to G, function G. All right, so let's do an example of this where we actually bind a value, bind a domain value to that parameter X for H. So what we're basically saying here is, let's say we want H of 2. All right, so that's going to be equal to F of G of 2, which is going to be equal to F of 3 times 2, which is going to be equal to F of 6, which is going to be equal to 6 plus 2. 6 plus 2, which is equal to 8. All right, so that's an example of functional composition. There's also an interesting functional form. This is a type of functional form. Whoops. This is an example of a functional form. Let's do another functional form. This is apply to all. All right, so apply to all. So the way apply to all works is you have a single function, you have a list, and the function applies, let's say the function is applied to all elements in list. All right, and so here's what it look like. We're going to define h of x as x times x. So that's our single function. And then we're going to use, by the way, the symbol we use for this is alpha. All right, so then we're going to say alpha h, and here's my list, 2, 3, 4. And that is going to yield, that is going to give us, as a result, that's going to give us, whoops, what? What do you expect that we're going to get when we're done? All right? So hit pause for a second, think about it, and see what you come up with. Okay, we're going to end up with a list with h applied to each element in the list. So that's going to be, whoops, that's going to be h of 2, h of 3, h of 4. So we're going to have 4, 9, 16. That's going to be our result when we use apply to all. Okay, so we've done kind of a brief high-level overview of the idea of functional programming and mathematical functions. And so what we're ready to do now is actually start doing some programming using Scheme.